Okay, get out your assignments and your book. We're going to go through these. The 5.1 practice, textbook practice.
The one day I never my physics book. It's like the one I didn't even do one.
If you need, I've got a couple spares here if you need to borrow one.
No. I didn't even.
You have not worn this once today.
I know, it's hot.
Okay.
Oh, dude.
Sure. You betcha. Okay, so I'm going to have you just grade your own here. And then I will collect grades. If they're in your notebook, that's fine. I'll just maybe collect them at the end. Yeah, you can just show them to me. Okay, so that's a possibility, sure. Well, we'll see. If we have time today, I'll get them, but maybe not. Maybe tomorrow. Okay, so let's go through these now. What was the assignment here? I got to look and see.
85.
85.
2 through 4.
85.
I don't know. Let me.
Oh, hang on a second. That's got to be. 1 through 3. Is that right?
Yep.
Okay.
I hate when it's like it looks so short. It's like A, B, C.
I know, lots of parts. Okay, here we go. Number 1. Describe in words the motion of the 4 walkers shown by the 4 lines in Figure 5.4. So look at Figure 5.4 on page 85. So let's see. Walker A. Jolie, what's Walker A doing? Describe in words. What's he doing?
Moving in a constant positive motion.
Say it again.
Moving in a constant positive motion.
Okay, constant positive velocity, probably, right? Okay.
I thought you wanted us to describe it because I said it came from origin and went from east.
Okay, and as long as you said, the key part here is moving east is great, positive means east, either one is fine. But what's the important part of that motion there that probably needs to include? Constant velocity, okay? Or you can say constant speed moving east would be fine too. No, it's not, because it's a position time graph, right? So it's not acceleration, it's constant velocity. Okay? We'll just make, how about, we gotta figure out how to do points on these. We'll make each of these worth like 1 point, just so you can grade it, okay? Walker 2, Walker B. What's Walker B doing? What's happening there? Ellie, Walker B, what do you think?
I would say moving in a constant negative velocity.
Constant negative velocity for Walker B? We wanna, say it again.
Oh, I was.
No, go ahead. You wanna fix it? You were looking at the other one.
Oh.
Yeah.
Isn't, can I?
Yeah.
Walking constant in the positive, at a constant velocity in the positive direction from the negative?
From a negative starting point, sure, exactly. So we see with Walker B, he's starting west of the intersection. So you could either say he's starting west or he's starting at a negative position. Either one's fine. Something that, as long as you can use your own words for that, that's why I don't care about that. But the main thing is he too is walking with a positive velocity, or he's walking with positive speed to the east, right? Either or, okay? Let's see here. What about Walker C? Walker C is a little trickier. What's going on with Walker C? What do you think, Mr. Brock?
Starting at the origin and decelerating to a stop.
Okay, he's starting at the origin and he's decelerating to a stop. In which direction is he moving?
Positive.
Negative. Okay, good. So he's moving to the west. The key parts are though he's decelerating, slowing down to a stop, right? Make sense? Okay. He's starting with a negative velocity, right?
Yes.
Okay, good. Okay, so 4 points apiece, just kind of, use your judgment. Describe the motion of the car shown in Figure 5.5. Okay, so what's going on with the motion of the car in Figure 5.5? What do we think here? Matthew, help us out. Number 2. What's that? Oh, we didn't do part D? Oh yeah, what's part D? Matthew, part D, take that instead.
Alright, so it came from the east and went west.
Okay, good. What about it's important?
Constant.
Constant velocity, good. Okay, very good. Okay, number 2, describe the motion of the car in figure 5.5. Figure 5.5. Tyler, what do you think? What's that car doing? Okay, it starts off from A to B, negative constant velocity, good. Then what? What's it doing from B to C? It's a rest, yeah, good. So it's just net zero velocity, right? It's stationary from B to C. What about from C to D? Does it not accelerate? What do you think? Constant.
Just abruptly starts and goes.
Okay, yeah, right. It abruptly starts, constant positive velocity, and then from D to E, this really would not be fun to do. It's going instantaneously from positive constant velocity to negative constant velocity. Not physically possible, but you get the idea. Okay, part 3, we're gonna get more questions about that. So we wanna know for part A. So once again, 2 is worth 4 points, 1 for each part of that. How about? Number 3, 1 point apiece. When was the car 20 meters west of the origin? Jordan, look at that graph, so 5.5. When was the car 20 meters west of the origin? We're assuming west is negative, right? East is positive. Between C and D, not between C and D. Somebody just give me 1 point, how about? Lucas, give me a point where for sure it is 20 meters west of the origin. If you need to scooch over by somebody, go ahead. Say it again. B, right. Because now look, it's a position time graph, right? At point B, look on the vertical axis. What's the y value at point B? Negative 20. That means that's the position, right? So what are all the points where it's negative 20?
B to C.
B to C. Yeah. B to C. Very good. Okay, so that was 1 point. Here's another point for part B. Where was the car at 50 seconds?
East.
30 meters east. C.
Good. 30 meters east. It's at point D, isn't it? Very good. Okay. The car suddenly reversed direction. When and where did that occur? Clara, when did the car suddenly reverse direction? Point D. Very good. Okay. Point D. If you said point D, that's fine. You might have said at 50 seconds. You might have said when he's 30 miles east. Any of those would be fine, as long as you're describing point D. Okay, moving on.
Page 87.
87, 4C, 6 through 8. Okay, good. So 87, 4C. Rank the average velocities from largest to smallest. So what's the largest velocity, Riley? What do you think?
Are we on which one?
We're on 4C, so it's figure 5.8 on page 87.
B and C.
B and C, they seem to be tied, don't they? Yeah.
I thought you were asking for the graph one too.
No, can't give me a numerical one. Yeah, just B and C. So those would be the fastest. What's the slowest? A is the slowest because it's at rest, isn't it? Good. And then so the one that's in between would be D, right? Okay, very good. Just make that worth, how about 4 points?
10 points.
10 point, no, 4 points. Then we had 6 through 8, right?
Yes.
Okay, this is kind of a good one. Chris claims that as long as average velocity is constant, you can write V equals D over T. Okay. Use the data from the graph of the airplane's motion in figure 5.6 to convince Chris that this is not true. What do you think? Ryan, why is that not true? How could you show Chris that he's definitely not correct about this?
He needs to factor in relative V and create this thing.
Good, because that's really not the definition, is it? Right? Velocity is change in position over change in time. It's not just position over time. We could look at a couple examples. I mean, if you just tried a couple, you're going to see you get different answers based on Chris's suggestion here. If we put D over T, at 1 second, what would we get? We would get like about 120 divided by 1. So we get about 120 meters per second. But if we go to point 2, we get something like, pretend that's on the 200. So we get like 200 divided by 2, or that's 100, right? That's different. But we can see from the graph that clearly, that's a straight line, so it's constant velocity, right? So you get, his idea is incorrect. Can anybody tell me, just as kind of, this isn't, however you pointed that out is fine, just make that a one pointer. But little extension of this, anybody tell me when Chris's idea might have actually worked?
Start from the origin.
Okay, if it started from the origin, right. If it started from the origin, it would have worked, wouldn't it? Okay, good. All right, so moving on here, just 1 point's fine. Number 7, so 7A, yeah. Use the factor label method to convert the units to the following average velocities. Okay, so if the speed of a sprinter is 10 meters per second and we want to convert that into miles per hour, what do we get? 22.37, so, or just say what they wanted to they give us. Okay, so what would it be in terms of the number of appropriate sig figs? And if you get it right, I don't care if you get sig figs. We're focusing on just the conversion. So what would it be? 22.4 miles per hour, that's fast. What about kilometers per hour?
36.
36, good. Okay, 36.0, very good. Part B, the speed of the car, 65 miles per hour into kilometers per hour. What's that gonna be? 104.6. So if we were going to, correct, but if we were gonna put that into, and that's fine, give yourself credit, but if we were gonna put it into the appropriate number of sig figs, what would it be? 100, yeah. What about meters per second? 29 to 2 sig figs, very good. Once again, don't select the sig figs on this problem, just give yourself credit if you did the conversion correctly. Speed of a walker, 4 miles per hour into kilometers per hour. What's it come out to be, roughly? Okay, so to 1 sig fig is 6, yeah. And meters per second? 2, good. Okay. Then everybody knows how to do that with the factors, just multiplying across. If you don't, when you can lab, see me when you go through that. Okay, draw a position time graph of a person who walks 1 block at a moderate speed, waits a short time for a traffic light, walks the next block slowly, then walks the final block quickly. I think we kind of did.
No, we never got to it.
Did we not? Oh, we didn't.
You didn't?
Yeah.
Question.
Okay, so
There's a whole bunch of other things.
yeah, let's do this one real quick. So read that one back to me. So we've got,
Yeah.
so position time, so what's the first part look like?
Walks 1 block at a moderate speed.
At a moderate speed, so does that look like a moderate speed to you?
Yeah, but all
Okay.
blocks have to be the same.
Same length, right?
Yeah.
Don't go too crazy.
Okay.
Waits a short time for a traffic.
Okay, look, shh, look please. Okay, he takes a rest.
Waits for a short time. for
Okay,
traffic.
so that's gonna look like that, right?
Yeah.
Now what?
Walks the next block.
Slowly.
Slowly, okay, but they're the same
Lower.
length, aren't they? So I have to go up the same amount, but I'm just gonna go at a shallower slope, so something like that,
Yeah.
Yeah.
right? And then what's he do? Probably ran out of
Walk
space.
fast.
The final block.
Oh, and he goes really fast, good. Okay, so the last block, he's just gonna go like that. Something like that, right?
Yeah.
Just that basic shape. Obviously, we don't have any numbers here, so you can't make it any more specific than just an average line, a flat line, a low slope line, and a high slope line, right?
Yeah.
Okay, good.
Onward.
Oh, onward and upward here, so,
We don't have to do 11 because we did that in class. So number 9.
that one, let's just say that one was worth, how about 4 points, 1 point for each part? Okay, number 11. Is that the next one?
No,
Oh, no.
number 9.
Number 9.
A. Sorry, I should.
Okay, so consider the motion of bike rider A in figure 5.7. Write the equation that represents her motion. Yikes, okay, so figure 5.7, bike rider A, we actually have some numbers here, don't we? Okay, can anybody tell me then, with this one, with bike rider A, what are the key parameters here? What are the things we know about bike rider A based on the graph? What's one thing we know? Okay, oh, what's the velocity? Good. It's the slope, isn't it? What's the slope of that line?
1.
It's constant and it's 1. Is that right? Everybody agree? It goes up. It looks like it goes
Yeah.
over. Okay, good. Yeah, it goes over. It rises by 2 and runs by 0.2, it looks like. So what's that gonna be? 10. Yeah, everybody see that? The velocity is the change in position over change in time. The change in position, it looks like it's positive 2 meters. The change in time is 0.2 seconds, right? 2 divided by 0.2 is 10 meters per second. So that's the velocity, right? Okay. What about the initial position?
-2.
Ah, okay, so initial position is -2 meters. And so now we can use the only equation. Oh, thanks. Here, I'll just come up here in case somebody claims it. Thank you. So then the only equation we know is position equals initial position plus VT. So what's that give us for the equation of motion then?
V equals -2
-2
plus meters
plus, and I don't even care if you have the units in there,
10
plus 10
times 10.
T?
Yeah.
Okay, good. On that one, okay, now here's how I want you to do that one. If you give yourself, if you did that one completely correctly, give yourself 3 points. If you did that one mostly correctly, you know, you had the right idea, but maybe you made a mistake or something, give yourself 2. And if you did part of it, but you didn't get to completion on it, maybe you understood, you got part of the information that was given, give yourself 1, okay? Let's see here. What was next then? 10?
10A. Oh, no.
Oh, we didn't do part B.
9.
Okay, where will the writer A be at 1 second? So we can tell that right from the graph, can't we? At 1 second, if we continued that forward, where would writer A be?
8.
Looks like 8 meters, because the slope is, he's rising by 2 meters every time he runs one of those 0.2 of a second increments. So he's gonna rise up from 6 to 8. Okay, so 8 for 1 point. Okay, so then let's see. 10. Consider the motion of bike rider C. Okay, what's bike rider C doing? What about C is the same? Starting point's the same, and so bike rider C has an initial position of -2 meters, but what's the velocity for bike rider C? Negative, is it the same slope, which is negative? Oh, 6.6. Yeah, so how are we gonna get that? So the slope, we're gonna have to pick 2 convenient points, right? So it looks like if we pick, -0, -2, and 0.6, -6 on there, right? So what's the rise is gonna be -4, and the run is gonna be 0.6?
Yes.
Okay. So it's gonna rise by -4 meters when it runs by, we said 0.6?
Yes.
0.6 seconds. And so if that works out to be, what is it again? It's gonna be like -6.6666, repeating, right?
Yeah.
So to what, 2, how many places do we have here? 2? I don't care if you rounded it correctly. -6.7 meters per second velocity. Okay. So what's our equation gonna be then? Good, -2 plus, or minus, right, 'cause it's negative velocity?
Yep.
Minus 6.7 T, okay, there's the answer, same deal as last time.
Is it okay if we left in the number 4 and 0.6?
That's fine, sure, I don't care, that's fine, if you left it like that, that's fine. We won't be doing that in the future, but for now, that's fine. But when we get into doing more of these problems, we'll talk about that. Okay?
B.
B, when will the rider be at -10 meters at this rate? Yikes. Okay, so we're gonna have to go, yeah, it looks like we're gonna have to go down. The rider, it took 0.6 seconds to go from -2 to -6. So we're gonna go another 4 meters in the negative direction in another 0.6 seconds. So where does that leave us again? 1.2. Okay, so the second part would be 1.2 seconds. Okay?
Oh, you guys are on 10 now. I thought we were, oh, I did that.
Okay,
I
and
thought
then
you said
11,
nine
did we do one of these in class?
You did 11.
Okay, so 11 is worth, let's just say that would have been about a 6-pointer. If you went through that in class, just give yourself the 6 for that, that's fine. We did that in class. And then did we do 12 also?
No.
Okay, so that's it, okay?
Oh, wait, we
Alright.
did
We didn't do
12.
12.
Oh, we did
But
do,
we
okay.
did do 12.
Oh, gotcha. Okay, so 12 was part of the assignment, good, so let's do 12.
Oh, I see.
Yeah. You see the confusion, see how that works? At the same time, the car in problem 11 left, a truck, oh, okay, so we gotta look at problem 11 then. Okay. Oh, yeah, okay, this is a good one, I like this one. So, let's take a quick look at this, we'll look at this one 2 ways, this is kinda good. Okay, so let's zip through number 11 again. If a car starts, it starts 200 meters to the west of town, and it moves with a constant velocity of 15 meters per second toward the east, right?
Right.
Okay, let's look at this on a distance, or a displacement, or a position time graph, sorry. So one way we could show that then is, let's say if this is negative, oh my goodness. If that's negative 100 and this is negative 200, the car is starting here, right? And it's moving forward with a velocity of 15 meters per second,
Yes.
okay? So then that's gonna look something like, depending on what our scale is up here, let's just kind of draw this qualitatively. I just wanna give you an idea what's happening.
Yeah.
So this car is gonna go forward like that, isn't it? Right? Now, let's look in problem 12. What's the truck doing? At the same time the car 11 left, a truck that was 400 meters east of town began moving west at a constant velocity of 12 meters per second, okay? So what's that gonna look like? So 400, that's gonna be way up here somewhere, right? Because now the car started off 200 meters west of town, right?
Wait, where's town?
So town is,
Town's the center.
so town's in the middle. So here was the town, right? Here's east. The car started over there, moving in this direction,
Gotcha.
and the truck is starting clear over here, starting east of town, moving west,
Okay, good, that's what I.
okay? And so we're ultimately gonna ask, when do they pass each other? But what's this look like on the graph? So this guy's gonna go clear up here to positive 400, and if he's moving westward, that's the negative direction, right?
Yeah.
With a speed of 12?
Yeah.
So it's gonna be it's not quite as steep a line, but what direction is it gonna be going? Downward, good. Okay, so it starts there. It's just gonna go down like that, isn't it? And so there's gonna be some point where, at the same time, they're at the same position, right? So that's our job, is to find that, right? Okay, so how are we gonna find that? Well, the way we find that might be easier than trying to manipulate this graph. Let's just look at it in terms of the equations, how about, right? So if we set up an equation for the car and an equation for the truck, what would they be?
-200.
Okay, so for the car, car's blue, isn't it? For the car, we know that D, I'm gonna call it D sub C for the car, equals its starting position of negative 200 meters, right? Plus,
15 times t.
yeah, good, the velocity is positive 15 t. Agreed?
Yeah.
Okay, now what about for the truck? Okay, the truck.
This is 12.
So the position of the truck starts off at positive 400. And it's gonna go at a velocity of negative 12, so minus 12t. Okay, how about that? That looks an awful lot just like a linear system, doesn't it? Right, instead of x's and y's though, we've got d's and t's, right?
And big old numbers.
But what do we know here? If we're trying to, we're starting to kind of see some of how physics can be useful here. If we want to know, okay, well, we drew the graph, didn't we? So that's done. Find the time and the place where the cars passed. So the deal is, though, they're going to be passing at the same time and the same position, right? Good, so we know that really DC and DT have to be equal, right? By setting those equal to each other, do you see that we're asking a question to the physics gods? When we set D sub C equal to D sub T, we're saying, okay, when are they in the same position? When are those two quantities the same, right? And we'll solve a math equation, and that's how they communicate back to us when that happens, right? So we just end up with, by setting these two equal to each other, we get negative 200 plus, what is this doing? Is this not bizarre? It's like it's like, I don't know, it's like there's some spirit living in my board or something. I don't know what's going on. So we get negative 200 plus 15t equals 400 minus 12t. And the value of t that we're looking for is the value when the positions are the same, right? Okay, how about that? So easy to solve. We just add 12t to this side, add 200 to this side, right? Everybody agree? So I'm going to get 27t equals, if I add 200, 600, right? And so t just equals, what's that going to be? It's going to be 2, oh, it's going to be 2, 2, 2, exactly, forever, isn't it? Okay, so to how many places do we have this here in this problem? Probably 2.
Because 15.
So 22 seconds, or if you said 22.2, I don't care about the units, or about the sig figs. But that's when it happens, right? After roughly 22 seconds, the car and the truck are gonna pass by each other.
I cheated and graphed it, so that's okay.
That's fine, I don't care if you grab, I don't really care. I mean, at this point, I just want you to know the relationship so you can get the answer, that's fine. So if the answer's 22, for the time, how do we find the position?
Plug it in.
Plug it into either one, right? Okay? Because we know that they're gonna be the same. At that time, they're gonna be the same. So probably the, I don't know, doesn't matter, top one maybe. So if I plug 22 in, we get negative 200 plus, and honestly, do I really wanna use, see, this is what I don't like about the rounded part of it. Sure, we rounded that time, didn't we? But in your calculator, you'd really be better off not rounding it and plugging in the unrounded version of t up here, right? Does that make sense? Either way, you're gonna get the same answer in this case, I believe. But it's, if we plug in 22.222, what do we get? What's negative 200 plus 15 times
133.
133? Okay, so we get roughly,
0.33.
so we get 133.333
But should
repeating.
we
And so,
change it to 130?
so it becomes, so when we round it to the appropriate number of sig figs, we get 130, right? I don't care if you did that. I don't care about the sig figs on this one, right? So it really should be 130 meters. So what's that mean if it's a positive 130? 130 where?
East.
Well, east, right, for us, because we're just traveling east-west, right? Okay. Make sense? Okay. That's pretty good stuff. This kind of gets us ready to think about the stuff we're going to do next.
Ooh,
So how many points was that worth? Somebody tell me how many.
5.
What was that last one?
Do we turn it in? I have it to be turned in.
Can you turn it in? Is it?
I can.
Is it? If you don't want to turn it in, if it's going to mess up your notebook, don't. That's fine. I'll just get scores. How about it? So the last one was worth. Good question. So the last one. Let's just make it worth.
10.
How about
21.
How about 4? 2 points. 2 points for A. 2 points for B. Okay.
So how many points total?
So how many?
I got 39.
You tell me. How many did you
I
get?
got 39.
39 total.
Ooh, that's random. Let's make
Wait,
the
you got
last one
39
worth
right?
5. So that
Okay.
we
So
get
everybody give yourself a freebie to make it worth
Yes.
40. How's
You
that?
wrote your name on it.
If you wrote your name on it, very good. If you wrote your name correctly, that's what it's worth. So it's out of 40. Okay, so how much time we got?
We have 15 minutes.
15 minutes. Okay, so here's what I want to do then. Let's go. Listen, please. So we're going to do on the, I want you to get a little bit more chance to work with that stuff, but here's how we're going to do this. Those groups are way too big. We're going to go groups of 2, and we're going to have half on, half off. So the people that are off can be working on the next assignment, which I will tell you. Have I told you the next assignment?
No.
Yeah, I'll tell you right now. what it's gonna be. And you can start working on that, we'll go in the other room. Those who are on can be just playing for the last 10, 15 minutes on the stuff. Try to get through some velocity times. So we had a couple, 7th period, we had an amazing, I mean, it was just like perfect. It was unbelievable. I mean, it was, so I had to say,
Like match the graph.
matched the crowd perfectly. It was unbelievable. So, I'll come around, I'll privately collect your points and that'll be it for today. So head
So
over.
we continue playing with that stuff?
Yeah.
Okay.
Oh, here's your groups. I'm gonna give you groups. So let's say we're gonna do, we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 22. Oh, how about that? Perfect. 24. So we're gonna do, can you what? Tell me, I didn't hear you. Tell me when we get in. You can pick your own groups, 2 per group, that's it. 2 per group. The first ones that show up over there are on today, the other ones are off today.
So what do we look if we're not on?
If you're not on, then you're working on the assignment, and tomorrow and Monday,
What
you're,
assignment?
the one I'm about to give you, over 5.2.
We give you the assignment?
If you can, that's great, yeah. Otherwise, I'll come around and get scores.
Can we just work on the assignment, like instead of?
Oh, yeah, that's fine, you can be off today, that's fine, yeah.
How much time are we gonna get in by next time?
Well, Monday's a little short, so you get the amount of time on Monday, yeah.
And tomorrow.
And then next week, we're gonna do our first real lab.
What are we doing tomorrow?
Tomorrow, oh, yeah, tomorrow's Friday, isn't it? I was thinking today's Friday, oh, that's
I wish
like,
it
I
was Friday.
hate that realization.
oh.
Hold on, let me track your phone.
I'm just kidding.
So tomorrow, we'll probably do more of the same. I'll probably give you guys some on and off time in the lab, yeah.
Okay.
How's that sound?
Gosh, you always do this.
So is this gonna be like a regular thing? On-off time?
Yes, yeah, for this group, this can be a regular thing.
So we're large.
Because, yeah, you guys are large and not necessarily in charge.
Oh. Here's your cookies, but.
Okay, thank you.
Hey, where's my hat?
That's a good question. You can't keep track of your own hat.